So in this lecture, we're going to continue studying hyperbolic functions. These were introduced in the flipped class video, and I mentioned then that these are important functions. They come up a lot in engineering in particular, and also physics and sometimes chemistry, so it's worth at least encountering them a little bit. So we've seen before, right, we've seen looking at functions like e to the kx come up a lot in all of the different sciences. So we've seen these from modeling population growth, for example, exponential decay of like radioactive isotopes, things like this. So we saw that we could define a combination of these, say the hyperbolic cosine, take e to the x plus e to the minus x over 2, and hyperbolic sine was e to the x minus e to the minus x over 2. And then we saw in the flip class video what the graphs of these things look like. So we'll just quickly recap that here without going through kind of where these graphs came from. But hyperbolic cosine basically looked like this. And hyperbolic sine looks something like this. And we saw that the hyperbolic sine is an odd function and hyperbolic cosine is an even function. I misdrew this. Let's redraw this. Here, I didn't get this how I wanted. So let's redo this. So we see what's going off here. So there shouldn't be approaching an asymptote. They should be going off towards infinity, which is what we'll see. So it should go something like this. So that's what our hyperbolic sine looks like. Now we can see some properties of this right away. So if we see hyperbolic cosine of 0, we said before that this was 1, but just to check this, well, this is 1 plus 1 over 2, which is 1, and hyperbolic sine of 0 is e to the 0 minus e to the minus 0, which is 0, just like our graphs show us, but that's how we check them algebraically. We can also check that these limits, we've graphed these, but we can go ahead and check the limits as well. So example, the limit as x goes to infinity of hyperbolic cosine is the limit as x goes to infinity of e to the x plus e to the minus x over 2. And then if we split this up, this is as x goes to infinity of e to the x over 2 plus the limit as x goes to infinity of e to the minus x over 2. Now that second limit goes to 0, so this just becomes the limit as x goes to infinity of e to the x over 2 plus 0. And we know e to the x over 2 goes to infinity, so this just goes towards infinity. And we can similarly do the other limits as well. So for example, the limit as x goes to minus infinity, the limit as x goes to minus infinity of e to the x plus e to the minus x over 2. We break this up into two different pieces. And now in this case, the first limit is going to 0, and the second limit is going to infinity. So this goes to 0 plus infinity, which is infinity, just like our graph told us. And similarly, we can go ahead and do the limits for hyperbolic sine. And we can see we break this up just like above. And this goes to infinity minus 0, which is infinity. And finally, the last one is as x goes to negative infinity of hyperbolic sine. And again, we just break this up into two pieces. And so this goes to 0 minus infinity. which is minus infinity, which is exactly what our picture, or our graph showed us. But that shows it algebraically as well. So now let's try, other than just the fact that the hyperbolic cosine is even and the hyperbolic sine is odd, let's get into some of the reasons we might call these hyperbolic sines and cosines. You can see they share some of the same properties that sine and cosine share. So let's recall one property that's important is the Pythagorean identity. So we have cosine squared x plus sine squared x is equal to 1. And this comes up quite often when we're working with sine and cosine. So we get a similar but not exactly the same identity for hyperbolic sine and cosine. So let's look at what happens when we square these functions. So we'll write this similarly to how do we do with cosine. And so this is e to the x plus e to the minus x over 2 squared. We can pull that 1/2 squared out front, and then I have e to the x plus e to the minus x squared. And now if I FOIL this out, I'm going to get e to the x times e to the x plus e to the x times e to the minus x plus e to the x times e to the minus x plus e to the minus x times e to the minus x. And notice when we simplify this, I get e to the 2x, and then each of the middle terms is 1, so I have 2 copies of that, so I get 2, and then I get minus 2x here. And similarly, we can do the same thing with hyperbolic sine. And so this is and same computation here. And then if we just go through and do the same computation, we're going to get this. Now notice if we look at these two things, there's a lot of these things, same terms in there. So we have an e to the 2x and an e to the minus 2x in both of them. So if I take the cosine squared of x, the hyperbolic cosine squared, and subtract the hyperbolic sine, I have 1/4 e to the 2x plus 2 plus e to the minus 2x minus 1/4 e to the 2x minus 2 plus e to the minus 2x. And now notice everything cancels except for the 2, so I have a 1/4, and then I get a 2 minus minus 2. So this just becomes 1. So our identity here is hyperbolic cosine squared minus hyperbolic sine squared is equal to 1. So not the exact same as the sine and cosine relation, but pretty close. Just have a difference there. We have a subtraction instead of an addition. We can also introduce the hyperbolic tangent function. So just define it exactly how you would expect hyperbolic sine over hyperbolic cosine. And so this, if we simplify, becomes this identity. And we can graph this as follows. In this case, this looks something like this. And that we do have asymptotes here at 1 and at -1, which you can check just by taking the limit as x goes to infinity as x goes to minus infinity. So that's a good exercise to check. So maybe check limit as x goes to infinity of tangent equal to 1, and the limit as x goes to negative infinity of hyperbolic tangent is -1. So maybe pause the video and take a few minutes to actually check those limits. So as you might imagine, we are going to want to take derivatives of these. This is calculus class. So it's not hard to do these because they're just combinations of exponential functions, which we already know how to take the derivative of. So if I want the derivative of hyperbolic cosine, this is just the derivative of this function. And so I can pull that 1/2 out front. So I have this derivative. And now we know how to take those derivatives. This is e to the x, and then by chain rule I have minus e to the minus x. And then notice this is exactly hyperbolic sine. So another derivative for our bank of derivatives is the derivative of hyperbolic cosine. It's hyperbolic sine. So similar to sine and cosine, we just don't have the negative sign coming out there. And similarly, we can take the derivative of hyperbolic sine, bring that 1/2 out front. And now when we take the derivative of this, derivative of e to the x is e to the x. And now when I take the derivative of e to the negative x, I get a negative out front, so that becomes a positive, and I get this, and this becomes cosine, hyperbolic cosine. So again, up to that negative sign, these behave a lot like sines and cosines in terms of the derivatives. Okay, so let's see one application of these functions. Okay, so we have a power line hanging between two towers, and it's in the shape of this curve given by t over w equals hyperbolic cosine of wx over t. T here is the tension in the cable at the lowest point, and w is its weight per unit length. Okay, so this curve is called a catenary. Okay, so let's see, what do we want to do with this? So let's suppose the cable Okay, so if the cable stretches between the points x equals minus t over w and x equals positive t over w, let's find an expression for the sag in the cable. So what is the sag? This is the difference between the highest and lowest point of the cable. Well, if we think back to what our hyperbolic cosine function looked like, remember it looks something like this. So its highest point should be over here at the edges, and its lowest point should be there at 0. So what we want for our sag here, let's call the sag S. So S should be f of t over w minus f of 0. And so if we plug this in, this is t over w hyperbolic cosine, and I have w over t, and then the x is t over w minus t over w hyperbolic cosine of 0, which we know that second one is 1, so this is t over w. And now if I simplify this, I just get a 1 in there. So this is, the sag is just t over w hyperbolic cosine of 1 minus 1. And the second thing we're going to do is let's check that this satisfies what's called a differential equation, which is an equation that involves the derivatives of the function. So let's show often in physics and engineering, you know a differential equation and you're actually trying to find the solution. In this case, we're just going to check that it actually, we already have the solution. We're just trying to check that it actually works. So if I take the second derivative of this equation, this should satisfy that it's w over t times the square root of 1 plus the first derivative squared. So we just want to show our y satisfies this equation. So we're just going to evaluate each side and see that they're equal. So the first thing to do is to take the derivative. So I have the t over w out front, and then I take the derivative of hyperbolic cosine, and I get hyperbolic sine. And now I need to use the chain rule to take the derivative of what's inside. The w and the t are constant, so this is just tw hyperbolic sine of wx over t. And now when I take the derivative of this, I just get w over t. And so that cancels with the w over t, or the t over w out front. And I get that the first derivative is just this. And now I'm also going to need the second derivative, because I was looking for that for my differential equation. So this will give me hyperbolic cosine. And then chain rule says I have to take the derivative of what's inside. So that will just be w over t. And I get this back. So now let's go up to this equation and let's compute the right-hand side and see that we end up with this left-hand side. So I want w over t, and then I want 1 plus dy dx squared. So this is w over t square root of, now remember the dy dx is hyperbolic sine here, so this is hyperbolic sine squared of wx over t. And now we're going to use that equation we had above that said hyperbolic cosine squared minus hyperbolic sine squared is equal to 1, which says hyperbolic cosine squared is 1 plus hyperbolic sine squared of x. So use that little identity we had above to rewrite this as w over t square root. And now we'll replace this stuff inside. And now that the square and the square root cancel. And notice this is exactly the second derivative. So it does satisfy the differential equation we wanted it to satisfy.